Okay, let us begin our seminar. I'm happy to greet everybody on our first seminar of this academic year. And today it's my great pleasure to introduce you Professor Anton Osokin, who recently joined High School of Economics, who did his postdoc in area of Paris with Francis Bach, with Simon Lacoste-Julien, right, and with Ivan Laptev. So now he's a professor in High School of Economics. And in today's talk, Anton will tell us about his recently accepted paper to NIPS. And this paper has got oral presentation. So just to know, orals are less than 1% of total number of submissions to NIPS. So there was about 3,200 submissions, and only 40 papers have got orals. And so this is one of those 40 papers. So I'm quite curious to hear what should you do to get NIPS oral.
Okay, thanks a lot. Okay, so this will be about structured prediction and about theory of structured prediction. So I'm not sure I will explain what should you do to get a NIPS oral, because this is kind of random. But and also what I'm not going to do, since there is theory in the title, you might have guessed that there are proofs inside, but I'm not going to tell you any proof. So basically my goal is to explain you what is done, what is done and why it is done, and not how it is done. How it is done, there will be some tricky moments which are below the curtain. But for that, for those, I'll address you not even to the paper, but to supplementary, which is 20 pages after the paper.
So you don't know it by yourself?
No, I know. Okay, so it's at some point I did know that when I wrote that. So and then I keep forgetting. So every time I forget. Okay, so basically the plan will be the following. First, I'll go word by word. So first, I explain what structured prediction is, just for those of you who are young enough not to know. Then I'll explain what I mean by theory of structured prediction, and then we'll go calibrated, surrogate, and so on. Okay, so let's start. So basically, what is structured prediction? Structured prediction is umbrella term, which is a subset of, which unites a subset of tasks of machine learning. So these tasks often usually require to predict many things at the same time. So basically there are many variables that have to be predicted. So this is very related to graphical models, but graphical models have to be probabilistic. They have to be some graphical model. And structured prediction, I like to think of structured prediction as something more general. It's not, it includes graphical models, but is not limited to them. So methods can be not probabilistic at all. They just have to produce structured outputs. So basically examples of data that is structured like that include sequences, tables, images, and so on. So now two examples of the tasks that are classical tasks for structured prediction. So the first one is image segmentation. So probably many of you have heard of this. So here input data is an image, and the task is to predict a label for each pixel. So clearly these labels have to be connected with each other, and neighboring pixels probably have similar labels. That's why modeling this structure and modeling these connections is very important. Another example is handwriting recognition. So let's say we have images of letters, and we have to recognize what the word actually is. So here also sometimes people write in such a way that recognizing individual letters is impossible. So basically we need to kind of use context to understand. This helps a lot. Okay, so in structured prediction, usually there are two very distinctive parts. At least when people write papers on structured prediction, usually it's either inference or learning. So basically I'll explain what these tasks are, because they will pop up always. They always pop up when someone talks about structured prediction. So first, inference. So basically inference is basically prediction. So we are given input data, and we are given already the model, whatever the model is. And the task is to combine data and model to produce output. So this can be formed as probabilistic inference. This can be like combinatorial optimization and something like graph cuts or like some more complicated methods. But the task is to produce outputs. It doesn't have to be like one single output. It could be distribution of outputs. But I guess for now it doesn't really matter. So the second component is learning. So in learning, we are given a data set, like usually labeled data set. So there is, for each item, there is input data and there are output labels. And the task is to like, process all of that and produce a model that can later be used to predict. Okay. So basically, like in structured prediction, like when people talk about structured prediction, usually that's what they want. They want something that works. But in the recent years, this approach has like dominated a lot, and usually like people concentrate only on that. But sometimes this has limits, so there is no understanding why something works and what to do like to make it work better. So we want not only that, we also like it's natural to ask guarantees. So like to ask something where we can provide guarantees on the results. So in this work, we are focusing like exactly on guarantees. So basically, like what kind of guarantees I mean, like what kind of guarantees would we want? For example, like the most, what I think would be like the best guarantee ever is like if you tell me like what accuracy you want, say like in expectation or with high probability, and I tell you how many iterations you need to achieve this. Then you have your method, you just run it that long, and then you get your guarantees.
Are you speaking about learning method or about?
Yeah, about learning. About learning. So here this is mostly about learning, and like I will kind of put inference aspect under the hood, but like if you don't understand how inference can be plugged there, you just ask me like when it's appropriate. Okay, so basically, but like of course, like to achieve this, we are going to kind of forget like the first part. So I'll tell you from the beginning that this talk is not going to be practical. So this paper is the first paper ever that I submitted without any single experiment. So basically, this is left as a future work, and it's still in this stage.
So this is a secret to get oral on NIPS, yeah?
Yeah, actually, like for this particular project, I don't have like direct comparison, but like one of my collaborators at INRIA, and that was computer vision conference. So like first, with the first submission, he has some theory, and he did some toy experiments to illustrate the theory, and he got rejected. And so all the reviewers, like no one understood his theory, they were complaining about experiments. So what he did, he just cut off experiments. And he said, it is a theoretical paper.
Smart. No one would criticize your experiments if you don't have any.
Yeah, and that actually worked. I think he got like a spotlight or something, so he got in for sure.
100% reproducible work.
Yes, like it's all there, there is nothing more than the paper, it's all written. Okay, so let's go. So basically, like, when we talk about guarantees, like, usually, like, the first thing that comes to mind, especially in this audience, probably will be, like, likelihood-based methods. Like, conditional likelihood and something like that. So basically, let's introduce some notation. Like, I'll try to be consistent, but I'm not super sure. But, like, I'll try to keep track of everything. So basically, let's say, like, we have input x, we have output y, and we have a loss L. And we are going to use this loss to measure accuracy of the predictions at the test time. So, and in structured prediction, typically set of all possible y or all possible output is exponential, and that's what make this structured prediction different from other tasks. So basically, one approach to train is to maximize conditional likelihood, so basically log probability of y given x, and with respect to model parameters theta. So if we have a model like this, if we already obtained the maximum, then, to predict, we need to minimize we need to pick a label that minimizes the expected loss, expected error. So if our model is correct, if at this stage we manage to get the model that is correct, this will give an optimal prediction, the optimal prediction. Okay, so what are the problems with this approach? First, it's we can never solve this exactly, and sometimes the solution doesn't exist. It does exist, but it doesn't correspond to the real model, and that's usually the case. And like if there is an error here, it's very hard to connect it with the error here. So that type of guarantee that I wanted, like in the beginning, like a guarantee on the prediction, like expected prediction error, is very hard to obtain. Basically, like I just don't know how to do it. So basically, and also like what I see as a drawback of this approach is that this thing doesn't care about the loss. So just loss, there is no place for the loss. So and so the training is the same for all types of different losses. Although like some losses might be easy, some losses might be hard, and like there is no, but training doesn't care. And also, like what I want to say that like to be able to work well for all possible losses, we have to get the distribution correctly. And getting the whole distribution correctly is hard. It's like not an easy task. Okay, so basically that's why like we didn't go this way. So instead, like we will go to something which is like frequentist, which goes like more, which goes together with the linear theory often, and like which is easier to analyze. And there are some of the drawbacks that I've mentioned and just not present in this approach. So basically here the notation is again the same, and basically what we want to minimize the population risk. So basically we want to minimize the prediction error directly. So here like my model, like I'm introducing the first assumption that the model is parameterized with the score function. So basically there is a function f that takes the input and produces a score for each possible label. So usually like these scores are maximized, so if you are familiar with graphical models, this is like negative energy. So energies are usually minimized and scores are maximized. So here it's more convenient to work with scores, that's why we'll be always maximizing the score. So basically, again, like here, like this function is usually like very hard to minimize. It's like cost non-convex, non-differentiable, and worse than that, it's piecewise constant, so there is no gradient. So it's kind of very hard to do anything. Piecewise constant because of the argmax inside. So basically, what usually is done, instead of minimizing this, like we take something else, which is minimized. This is like usually called population risk, and this is surrogate risk. So basically, instead of the real loss, there is a surrogate loss. So basically, like to give you an example to connect with what you should know, like one example of surrogate loss is like a structured SVM loss. Another one, so basically to recover the conditional log likelihood method, maximum conditional likelihood method, we can do like this kind of log loss. Okay. So basically, like in this formulation, like where is the structure? So the structure actually appears in two places. First place, that the loss is structured. So what do I mean by structured losses? Like for example, like Hamming loss is structured. Like block zero, like as a counterpart, like the most unstructured loss is 0-1 loss. When you say like give a penalty of 1 if you predict incorrectly, and give a penalty of 0 if you predict correctly. Another loss that like I'm going to work with is a block 0-1 loss. Basically, it's like all the labels are split in blocks, and within if you make an error within a block, you don't make an error. The cost is 0. If you predict a label from a different block, error is 1. So this is also like superstructure.
And then Hamming loss is simply a particular case of block 0-1 loss.
No, it's not. Like it's different one, but it's so basically Hamming loss. Like first, it has like more assumptions. It assumes that there are the labeling consists of pieces. Say like pieces like multiple binary variables, and then you count how many errors you make in these binary variables, and it's not the same. So basically, like the block 0-1 loss take value, it's either 0 or 1 always, and Hamming loss like it can be like 0, like 1/3, like 2/3, and 1, like if you have like 3 variables.
I would say 0, 1, 2, or 3.
0-1, okay, but I always normalize to 0-1. Yes.
Excuse me, what is argmax? Argmax over which variable?
Over scores. So basically, f takes x as input and returns a vector. Like a dimensionality of this vector corresponds to the number of y's. That's a huge vector. And then argmax is like with respect to the indices of this. So basically, we can look at this as y. It can be the index of f, and then just picking the maximal element.
Okay.
Okay, so this is the first place where the structure is. That's the loss. and the second place is the scores. So in the world of graphical models, usually like scores are assumed to be factorized. So basically scores are represented as a sum of certain things, and these things, like potentials, they depend only on a subset of variables, not on all of them. So basically, that's why like usually like I will assume that set of allowed score vectors is constrained and belongs to something. So it's like not all the scores are possible. So we'll go further, like further speak about these constraints. Okay, so basically, like when we like look at this setup, what are the issues that we have to deal with to be able to like show something? What are the problems? Like first, like we are minimizing not we are solving this optimization problem, but we want to solve this. So this like there is like a mismatch between the two functions, between the two objectives, and this has to be like dealt with explicitly. And actually, like about this, I will be like talking most of the remaining talk, most of the time. So basically, then the second problem is that there is like we are always working with a finite data set. There is no such thing as infinity in practice. So basically, like also something has to be done to take care of that. And second, like there is always optimization accuracy. So basically, optimization errors. So normally, like we cannot solve this exactly. So there will be like some optimization error there. So basically, in the like theoretical setup that I'm going to tell you next about, I will take care about all of that. So basically, I will be able to give you exactly the answer to the question I put in the beginning. So basically, what is the number of iterations to get this test error, like in expectation, like the real test error? Well, I will be always dealing with the expectation, but it can be modified to high probability bounds, but I haven't done that. Okay, so what's roughly the approach to address these issues? So usually in the literature, like this kind of stuff, this kind of problems, issues are addressed with consistency. So this is like a keyword for that. So consistency basically means that minimization of this, like in the limit of infinite data, leads to minimization of this. So this property is very well understood for binary classification. It's like a kind of closed. Like the next slide, I'll tell you like what is the situation for binary classification. It's kind of studied for multi-class classification, like with multiple labels. Like there are some results there, but like no one has ever looked at this like in details for structured prediction. Okay, and so basically like for this one, actually like the standard like the field that deals with it is linear theory, and like for this one usually there are like a lot about optimization methods. But like to kind of simplify the approach, because most of my focus is here, I want to use the simplest approach possible. So I will be using like online SGD, so which deals together with both with finite data samples and like optimization accuracy. So like I assume that I will do like only one pass over the data set. And
so that empirical risk is unbiased estimate for the averages, if you're making just one pass with data.
Yes. Well, I wouldn't say this because like you're modifying your estimator like on the way. So basically, but you're not. You can assume that like each time you draw a sample, like to do a step of SGD, you get like fresh samples always. And that's why
you can
doesn't
get
it mean that
on the regret bound if you use online SGD.
only yes, but that's what I want. So basically, I want to bound like how far I am from the optimum. That's regret bound. Okay, so we'll get to like more specific like formulations. What will be there? Okay, so basically let's go back to consistency. Like first a binary classification. So in binary classification, output basically is binary. There are two possible values. Usually it's -1 and 1, and the loss is 0 and loss. So basically it's just 0 if there is a match between the prediction and the correct label, and 1 if there is a mismatch. So again, then the population risk is usually written in this form, and like this is like the surrogate. surrogate risk. And the key quantity becomes basically the product of the label and the score. So there is just one score. So basically, like this theorem, like of Bartlett et al. From 2006, but okay, sorry, like for the colors.
It's just because of the theorem.
No, it's like it's not supposed to be like that. It was not supposed to turn off at the first theorem I started talking about.
Slowly switching to the sleep mode.
Yeah.
What's your
No, basically, okay, let's focus. So basically, but this like results goes back. Credit goes not only to these people, but to many people around, because this was a hot topic back then, and many authors like did stuff. This is like just one particularly famous paper. So basically, what the result says, that if the surrogate is convex, well, we usually want convex surrogates because we want to be able to minimize with guarantees. So then, if it is differentiable at 0, and if the derivative at 0 is less than 0, is negative, then this surrogate is classification calibrated, and that's the notion of consistency. So basically, it means that minimization of this in the limit of infinite data will lead to minimization of this, like under this constraint. So basically, what are the examples of the surrogates that satisfy this constraint? Basically, like mostly all methods for binary classification that you know. It's like it can be like exponential loss, it's hinge loss leading to SVMs, it's logistic loss leading to logistic regression, like truncated quadratic loss, like all of them are like that.
So again, you said that F is classification calibrated, and that means that in the limit, optimizing the surrogate loss will lead to optimize in the real loss, the population risk. Are there are many different functions? Is there a way to quantify which one is better in terms of rate of convergence, for example?
So basically, that usually like these papers never touched this issue. They didn't care. Basically, so basically this goes to like the second the second and the third options, like was like the optimization accuracy. So basically, like the standard approach is that just you take any like online SGD method, the risk convergence rate for that usually. Then like its convergence rate depend on certain constants. Then these constants will depend on your loss and some properties of your data. And then like you just compute that constants, and like you're happy, like if you can compute that. Yes.
What is the functional class we have here?
Like in the the default like standard way, it's just all measurable functions. Then like those can be approximated with universal kernels. So you with that. So and basically beyond that, like notion of consistency is not really applicable because it's hard to like kind of. So basically, it's hard to push more complicated dependencies between the scores and the input, like through the theory. Just things break. So basically, I have to admit that there are people who try to do that, like Igor Steinwart, like Tong Zhang, if you know these names. But like to say the truth, I wasn't able to understand those papers. So like I don't know. So but they claim that there is some progress, but usually it's not really like used.
So what is the statement of the theorem? Is it that the minimum of the first function equals the minimum of the second function?
No. So basically, if you are at a minimum of this of the surrogate risk, then you are at the minimum of this one.
Okay.
There's an implication.
Okay.
So basically, like there is nothing is said about the uniqueness of those minimums, and like okay. So basically, like what do people do when they go to multi-class case? So here, like there is like a very important notion of calibration function. So what is calibration function? So basically, calibration function tells you what is the minimal possible excess of the surrogate loss, of the expected surrogate loss, given that the excess of the expected real loss is big enough. So basically here, like epsilon is the parameter, it's like how big is the excess of the real loss, and then like this quantity shows the excess of the surrogate loss. So I've written the exact definitions here, but like I'm not sure if it's like super useful to parse them, for you to parse them now, but this is like the key intuition, is that it says like how big the excess can, like how big the expected surrogate loss can be from its minimum if the excess of the real loss is big enough.
And what
What
is
is
Q?
Okay, Q, like this is simplex, so Q is probabilities. So those are like kind of posterior probabilities
Probabilities of what?
of labeling. So this is like a vector like of length, like of dimensionality equal to number of labels, and then it's like those are like greater. Those numbers are non-negative and sum to 1. They could correspond to some probability distribution over labels. So basically, this type of analysis is called like point-wise analysis. So basically, we assume that there is only one data point, and then it's like a worst-case analysis. So what's the worst-case distribution and worst-case scores, such that this will be true. Basically, yeah, of course, like there have been like at least several papers that criticize this kind of analysis and like claim that it doesn't capture the reality. Yes, that's true, but like there is not really, they don't really offer something else. So it's hard. This is already getting hard enough, but like going beyond is even harder. That would be like super interesting, but I think that's like a task for real statisticians, for people who like can go for this.
It's definitely not us.
And not me. That's for sure. Like while doing this, I've understood that I'm not a mathematician. It's kind of hard. Okay, let's go like to some examples to give you like what this like a calibration function looks like. So basically, consider like the Hamming loss. So basically there are two losses. Like this is like for Hamming loss, and this is for mixed block 0,1 and 0,1 losses. Like a basically mixture with a mixing parameter of I think 0.2. So basically what this shows, basically this is epsilon and this is like h of epsilon. So basically red lines correspond to situations where f is the full space. Like curly f is the full space, so basically there are no constraints on the scores. And blue lines corresponds to tight constraints on the loss, on the scores. So basically like here, so like this is for the quadratic surrogate that I'm going to introduce like on the next slides. But here like basically this is the span of the loss matrix, like in this case, or a span of the loss matrix of the Hamming loss. It's like super low rank. And then like here, this is the span of the block 0,1 loss, which is also like super low rank. So basically what I want to show you, that these functions are always non-decreasing, they go up. So basically they can be non-continuous. They can be super nice, like quadratic function like this. So basically, what is important? So basically, these functions can completely characterize consistency. So basically, if this function is greater than 0 everywhere rather than 0, then like situation is consistent. So there is like a result like from this guy, like Tongzhan 2004, like saying that. So basically, these functions are consistent, but we can see that they can be like very different. Like speed of convergence can vary a lot. And here, like this, like blue situation is not consistent, and this like is consistent. But again, like this plot illustrates that sometimes inconsistent functions can work better because they can just converge faster to somewhere.
Once again, why the blue curve is not consistent in the second case?
Because it's 0.
Because it's 0, like up to 0.2.
And what? It's good?
It contradicts
No, it's not.
Jürgen by John.
No. So basically, look, like we can just look at this function. So basically, let's say like say like look at this curve and like epsilon 0.1, so it's equal to 0. So basically it means that, what does it mean? Okay, so basically it means that there exists like 0 here, such that the excess of the loss is at least like 0.1. So that there exists f and q such that like this equals 0, and like this is big.
Isn't monotonicity is not our goal? We just want to.
Yeah, like this is monotone by default, by definition. So this is like always monotone. Because when we are increasing.
No, I mean the correspondence between two delta phi and delta L. If you decrease delta L a bit, you definitely decrease delta phi.
Oh, it can stay the same.
But it's not always the case.
Yes. So basically, like when like.
It seems that is our real goal.
Yes, you're right. So actually, like this kind of monotonicity, it implies consistency. So, but this is stronger than consistency. So usually, like when people talk about consistency, they don't like ask monotonicity, but this one is just stronger. Because, for example, okay, so like I think like when it like this function is strictly increasing everywhere, it is monotone. But like this transfer, like this calibration function can go like this. It's like it doesn't have to be convex. So basically, then it's not there is no this monotone dependency, but like situation is still consistent and everyone is happy. But maybe it's actually a nice way to look at this as monotonicity. It's like a bit simplifying. Not all cases will be covered, but like that's fine. Okay. Basically, let's move away from the plots. So basically, like here I wanted to say what I've already kind of tell you, like what's the connection of this to like the guarantees and the like optimization. So basically, if we are able to optimize their excess surrogate to up to accuracy h of epsilon, then we are guaranteed to have excess of the real loss below epsilon. Because this can be easily seen by a contradiction, because if this is not the case, if this one is like a difference between this and this is bigger than epsilon, then we have to be like bigger than the calibration function, just because it's the minimum already computed. So basically that's again like the result of Zhang, that like if this function is greater than 0 everywhere, rather than 0, then like the surrogate is consistent. So basically then the next question basically that we posed like when started looking at this.
Wait. What is delta L? Delta L is the difference between RL and the optimal point and the point F.
So basically, delta small l is the difference between the expected, like with respect to Q, real loss and the minimal possible real loss.
Okay.
So that's like kind of like we want to minimize this. Like if we like that would be like the real.
So the minimums are achieved in different points, in
Yes.
delta phi and delta L.
Yes. Exactly. Okay, so basically then the question is like what can go wrong if the situation is already consistent. So basically, is consistency all what we want, or we want something? Is it enough or not enough? It appears, like because like for like usually, like in all this of theoretical works, when people get prove that something is consistent, then it's done. Like it's happy. So like solved, problem solved. Especially, this appears to be kind of true like for binary classification. Then it's okay for multi-class classification when the number of classes is not too big, but it's not enough for like structured prediction. So basically, what can easily happen is that this calibration function is very small, like exponentially small. So basically, how this can happen is it's just the like a quantity which is like inverse proportional to number of classes appears at the beginning, and usually it appears in all the like existing calibration functions, and then like it's like this is so small, this is very small, and it implies that in practice we can never actually reach reasonable accuracy and bounds are useless. because we can never reach very small accuracy because of two reasons. Like first, like a finite data set, and then finite runtime. Like we cannot do like exponential data sets and exponential runtime. So basically, like to proceed, basically to do something with this, we have to like kind of like up until now, like we were very general. We were working with like any surrogates, but like for any surrogates, it's kind of impossible to compute this. So like what people usually end up doing with, they just prove that this is greater than 0, so consistency. But because now like the consistency is not enough, like we want to look at the constants, we need to actually compute these quantities, and then doing that for like general surrogates is just not possible. I don't know how to do it. It's like too hard. So basically, like what we do and what people usually do, we go for these squares. So basically, we look at the quadratic objective, like the simplest possible objective one can have, and then try to get the complete picture, like with that. So basically, all the results I will present next will be about this like quadratic surrogate. So basically, let's look what this surrogate looks like. So basically, it's just we are kind of regressing the loss. So basically, f is our scores, and we want to regress the negative loss with the L2 error. So like also like
But
we
if you regress, why is there plus but not minus?
because we are maximizing the score. So we want to have the score which has the smallest possible loss.
Which is minus L.
Yeah, which is minus L. Yeah, so like we can add like constants there, but it doesn't really matter. So like just like this form of writing this minimizes the number of symbols like that we need to use. Okay, and so basically this is like one form like of structure that we have is L, and another important assumption is that we assume that modeling assumption that like we assume this form of factorization of f. So basically there is the capital F, which is like kind of design matrix. So it's like a fixed. It's like it's the part of the surrogate. It's not. We don't optimize over that. And then like there is theta, which are like real parameters which depend on x. So you can think of this as like some form of factorization assumptions. So basically this matrix is typically very low rank, and it's like very tall matrix. So it's very long, like the number of rows corresponds to the number of labels, and then like number of columns correspond to number of actual degrees of freedom. So we have way less degrees of freedom than labels. So basically only like combining structure here and structure here will allow us in the future to get away from this like exponential quantities in the calibration functions.
What is this Gothic f? Is it the same as just usual f or not?
Because this is the function and this is like a vector.
Function.
A vector, so it's like a kind of. Yeah, but you like what I'm gonna do, I'm going to just plug this into this as a regular f. And then like we'll care about dependency on theta.
Excuse me, what is K and what
K
is
is number of classes.
You mean this exponential?
Yes, like K is exponentially big number and like which we like afraid of very much.
What is L colon Y?
So L basically is a loss matrix which is K by K. It's like a huge matrix, and this is like one column of that matrix. So basically those are all the losses if the correct label is Y. I'm using like a MATLAB notation. Okay. So basically let's like for that kind of surrogate they're using this for a purpose, that for it we actually can compute some calibration functions. Which is like I'm not showing you any like proof techniques how to actually compute this. It's like I'm not super proud of this. I'm proud that those were possible, but like how this was done is like I would prefer to improve these proof techniques a lot. Okay, so basically let's like as we start with, of course, with the simplest like loss, like 0-1 loss. So like let's see like what happens. So basically here the calibration functions will be like quadratic functions epsilon squared over 4k, where k is like number of classes. So this is like exponentially small and like kind of intractable. But this is expectable because like 0-1 loss is in some sense like worst case, like worst possible loss. So like it's like we have to like there is no structure there, so we cannot exploit structure at all. So basically, let's go to the next loss, which is like a block 01 loss. So here, let's say we have k classes, and S is the size of the blocks. So for example, we have like...
can the blocks intersect?
No.
And
So-
should the blocks form the full covering?
Yes. Like also like let's assume that the blocks are like of the same size, like, for simplicity. It doesn't really like these subfunctions I can drop, but like it doesn't really matter. So basically, like in this kind of loss, we will like I think this is like in some sense very structured if there are a lot of labels and there are very few blocks. Say like there are millions of labels, but those are like split in 2 blocks. So it's kind of like should be very similar to just binary classification, because the real task would be to classify between blocks and not between labels. So basically, the less blocks you have, the more structure you have in some sense.
What is a block?
Like just subset of labels.
What is block 01 loss? Probably you should repeat it again. I'm afraid it's remaining clear.
Okay, let's use this thing. So basically, here are ones, and here are zeros. So here are like 3 blocks, and this is like a matrix of size k by k. So it's like the simplest structured loss we were able to come up with to start operations. So basically, and like intuitively, when you look at this, it seems that the real kind of like measure of complexity of this loss is number of blocks and not the number of labels. So we don't really care like what is the number of
So
labels.
effectively it corresponds to the multi-label classification problem where the number of labels is the number of blocks.
Yes. Okay, so basically if anyone would solve like this a problem with this matrix, with this type of loss in practice, they would immediately merge the labels and just use the number of
Right.
blocks.
Right.
Yes. So in some sense, this is what we want to see this being like super easy, like in our analysis.
Yes.
So basically, and like now, like the very unsatisfying fact for me was that if you just compute the calibration function for this kind of loss, then you still get something very small. So basically, you win at most factor of 2, which is like not satisfying at all.
Maybe you should restrict somehow the family of phi.
F. So yeah, that's exactly what we are going to do next. So basically, here like the point is that just having the structured loss is not enough. So basically, even like for the simplest structured loss you can think of, like analysis doesn't react on that.
Yeah, but you need a different kind of surrogate functions, I believe.
Yes, so basically what we are going to do next, we are going to put more constraints on F. So F is like in some sense part of the surrogate loss. So we are going to do that. We are going to like use more specialized surrogate. So basically that's exactly what's missing. So basically if we add constraints on the scores such that we require that the scores live in the span of the loss matrix. So basically scores within the blocks are equal always. So we get exactly what we want. So we got like the calibration functions becomes O of 1 over D. So where D is the number of blocks, which is like an effective measure of the complexity.
So again, to achieve this, you need to ensure what?
To ensure that basically this set is defined as a subspace, and this subspace is a span of all the columns of the loss matrix. So basically linear combinations of the loss. So of course,
And the loss is
this. So here it will essentially be that all the components within the block are equal, because you can never make a difference between them.
But doesn't this mean that the problem becomes exactly equivalent to this G-label classification? That we simply unite all these
yes and no,
equivalent
it's kind of equivalent, but the objective is slightly different. So basically, like for us, this was mostly like a test that it should pass. So if this doesn't work, then like what do we hope for the more complicated losses?
Okay.
So you can look at this as like a test, like a sanity check. It works. So we get this. I'm not suggesting to use this for real applications, like for this kind of loss. Okay, so basically then like we were able also to derive everything for Hamming laws, which is more complicated. And actually like here like the story is the same. So basically if there are no constraints on this course, then we get something like very small. So it's not exactly this, it's like a slightly more complicated function. So basically like here it's exactly that, like a step functions with step that I showed you at the beginning. It's like from here. It's like a kind of a nasty function to derive. But if we add constraints on this course, here like constraints obviously are that the scores are separable. So their score can be represented as a sum of little scores which correspond to individual variables. Kind of energy style factorization.
With the factors of what size? With just unary factors?
Yeah, just unary factors. So
But again, this is not too interesting.
well,
There's no structure in this code, right?
no, this is structure. So basically, this actually like makes a lot of sense. Why? Because if you have a Hamming loss, then what you want to, like, if you had access to like complete probability, what you would do, you would just compute the marginals and take the maximum of marginals. So basically, if all the like this is like suggests us to do like exactly that, to just derive individual functions for these marginals and just do that.
What's T?
T is the so basically here, like for Hamming loss, to define Hamming loss we have to like kind of define variables like kind of a sequence of variables. Like sequence is not really there, like a set of variables. There are T variables. So basically T equals the log of K. So basically 2 to the power of T equals K. So basically we have like T binary variables, and the number of all possible configurations is 2 to T, which is K. So that's why like this T is much smaller than.
Can we say that this is also the number of unary terms in our energy?
Yeah, that's that. Exactly.
And again, it's essential condition that our score function cannot contain, say, pairwise terms or high-value terms.
Well, okay. So basically, that's what like I will get now. So basically, like these quantities are like exact quantities. So basically, if we change, so basically these quantities depend on the surrogate, on the loss, and on the like family, like on the constraints, on the family of the scores. So basically, if we change on any of this, like this can change. So especially if we are adding like kind of more relaxed factorization, then we are kind of increasing like subset of scores, subspace of scores, and then these functions can only go smaller, which is like not what we want. Basically, next step is like our like most positive results. So basically, I'm not expecting you to parse this theorem in details, but like I'll tell you just what it means. So basically, we have a lower bound on the calibration functions, which applies only to consistency cases that are consistent. So basically, like family of the scores are like big enough. So basically, by big enough, it means that they contain the span of the loss matrix. They cannot be smaller. It's basically that. And then, like for any f, like this kind of quantity appears. So it's a projection operator of the vectors which contain all zeros except two positions. One position is 1 and another position is -1. And we kind of project these vectors on the subspace of scores, and then we measure those. So basically, and this appears to be like the lower bound. So and the lower bound of this, like this quantities can be upper bounded by 2. So this is this function as was the calibration function for the 0, 1 loss is the lower bound on anything.
And you say that it is an optimistic bound?
Yes. Because because actually this quantity can be like very small, or not very small, like very large in some sense. So basically, for example, what are the properties of this bound? If you compute this bound for Hamming loss, for block 0, 1 loss, they match the exact values. It's just exact.
But for Hamming loss, we had epsilon squared divided by t.
Yes. So basically, here we will have this quantity will equal to k divided by t. So k will like cancel out and like just we will get like with the up to some constants we get. We get what we want. So in some sense, this bound, like for the losses that we can compute exactly, this bound gives the like good values. And also, what does this bound suggest? So basically, it suggests that of course, like this subspace of scores, the smaller it is, the better. Then it says that. But like just being low rank is not enough. So like one of like when we were like searching for like something like this, like one natural assumption was that just take something low rank and it will be fine. But being low rank is not enough. Like even for like the loss like of the smallest possible rank, you can always like get bad directions and it will like just destroy calibration function. So basically, it has to be low rank and aligned. Basically, not aligned with specific directions in the space, so that projections are small. So basically, again, like all I can say about this result is that it works for block zero and loss. It works for Hamming loss. Of course, like it works for regular zero and loss.
The bound is tight.
Yeah, the bound is tight. And all like this bound, like if we try to apply the same bound for non-consistent case, we just get zeros, so like useless bound. So it doesn't say anything useful. So basically, like one interesting direction for the future would be like more precisely characterize this. What happens to this when we try to change the subspace? Say basically when we are starting to add directions, like all we know for now is that this bound is not going to go up; it's like going down, like the bad direction. But like how fast will it go? It's not clear. Yes.
What is delta I?
Delta I is basically a vector with all zeros and one position I. Like.
Okay.
Yep.
What is the physical sense of this PF times delta J? Could you please?
Yeah, so that's projection of this like direction on the subspace of scores. So basically, it's kind of you are searching in which direction you can make the biggest kind of error.
You mean how the score will change? You will switch from I label to J label?
If you yes, if you move in that direction. So basically, if you start moving in that direction, what will be?
Oh, but we're in a discrete space. We can't just start moving in that direction. We
Yeah, but like
switch the
in
labels.
terms of scores, in terms of
And the scores are
The
assigned
scores
to
are-
different labels.
yeah, but the scores are continuous, so we can move in the space of scores. And so basically, if we start to moving scores in this direction, like in some sense, we are moving the excess of the real loss with some constants.
This simply means that the score cannot change too much if we switch just one label. No.
No, in some sense, we can switch labels in the sense that like our vector of scores defines which label we predict.
Yes.
So basically, because we pick the maximum
Right.
the maximum value. So basically, yes, if we switch the two or like move in the direction to switch the two, like what will be the difference in the surrogate? And so basically, if the difference in the surrogate is big, then like we get like this quantity gets big, and then like the bound is big, and then we are happy.
No, vice versa. If it is big, then this minimum is.
No, I mean like
low
the
value.
whole thing. Okay, yeah, this has to be small. Yes. So like this like things in the denominator have to be small.
No, we. Why
In
small?
denominator,
Yeah,
small.
the denominator has to be small, then the whole thing is big, and
Yes,
then the bound
that's
is
good.
big. So we want this to be like as big as possible.
And this
Big
sounds
is good.
very reasonable. Yeah. So now the question is, why it is small in case of Hamming loss, for example? What is the intuition?
What do you mean, like the intuition? It's exactly that. So basically we.
But why? Why?
Yeah, because in some sense with these losses, like the subspace in this like high dimensional space is equally distant from all their all these directions, all the delta ij, so it's like somewhat in the middle, and it's like far from them. And that's why I'm sorry, I don't really have like more intuition. I can only say that projections are small, but like it's repeating the same thing.
I have a feeling that it should have very clear physical interpretation.
Possible. Maybe. But like in some sense, like if the loss is low rank and somewhat symmetric, so basically kind of all these quantities are like equal, then like we have hope that the bound will work well. And if there are like some bad directions which are aligned well with one of the deltas, then like it won't really work. Okay.
So come on, we're talking about directions. There are no directions. F is simply vector.
Yes, but like the delta ij is a vector, is like some direction. So we are projecting these directions on the subspace of scores, like those vectors on subspace of scores. Yes.
Can you explain why they should be small? Like, why
Okay.
is it
We want this like so basically
Why-
like in the very beginning.
I mean the projection of the.
Yeah. Okay. So we want this bound to be big. We want calibration function to be big. Yes.
I understand this, but I
Okay.
don't understand why in the good case these projections are small. Because I think I don't understand what is this, what these projections are.
Okay. This goes deep. So basically, I don't have. So basically, I can explain connection between why we want this to be small, but why they are small in the good case, that goes into the proof. So that like I don't have extra geometric intuition for that.
Yeah. What is this?
Well, there is like a subspace of scores, and then there are like very like specific
When you
directions.
say subspace of scores, you mean like a vector of length k?
Yes, like all scores are vectors of length k, but
from
then
some subspace.
they live in some subspace. Yes.
Yeah. Okay.
And then like there are certain directions, certain vectors in certain directions that we project on this subspace, and we want those projections to be small, because if the subspace is aligned well with some of those, so like the projection is big, then like small change of scores there leads to big change in the surrogate, in the excess surrogate, and then like this is small. Yes. Okay.
Is it right that they don't have to be small, all of them, but only
Yeah, like
there should
one-
be at least one of them,
Yes.
which is very small.
Yes, that's the consequences of the fact that we are doing like worst case analysis. So basically, one bad direction is enough to kill the calibration function. So it's like, that's the property of this analysis. It's always like something like that will appear.
One bad ship spoils the whole pride.
Yes.
Right?
Exactly. Okay, but like in the defense of this analysis, like, I have to say that in most like realistic losses are somewhat symmetric. So basically, there are like for example, ranking losses are will be like somewhat symmetric. So there will be no like very specified direction. So it's kind of there are some symmetries, and the more symmetries there are, then the less that matters. That there are like some specific directions. Okay. So basically, as I said, this bound suggests that like the good losses will be like low rank, and then like they should be not only low rank but like aligned in a specific way, in the subspace. Okay. So basically now, let's assume that we are done. So basically, I've told you all I know about calibration functions. So I have this bound which I consider as very optimistic results. And I have a bunch of other pessimistic results, but let's say we can compute the calibration functions. So basically, is this the end? Is it are we happy? So obviously no, because I've kind of cheated you a bit. So I've defined the scale of calibration function arbitrarily, and it's I multiply my surrogate by a constant, any positive constant, and then my calibration function is multiplied by the same constant. And then all this kind of scale, notion of scale is not defined. So basically I've put 1 over k there, and it's kind of my choice of what is a natural scale, but it's not it's not. I could have put 1 there, and then like there will be no notion of 1 over k. So basically the next step is to actually like try to define the scale. Like what is the scale? Like how to get the scale right. So basically, and the approach we took to do this is to connect to actual optimization convergence rates. So because like when we start changing the scales, all the constants that appear in the convergence rates change, not all, but some of them change. And then like we need to have like a compromise between all these things. So basically we want to have like calibration functions in the right spot, and like all these constants not to kill the rate. So basically, you have to be like very careful to present to get the final result. So basically, what we are going to do is to actually like take like the simplest algorithm I know, like for which will be like average SGD, like to minimize this function, like in like online way, and then try to apply the rate there. So basically, like here, like to do that, to start doing that, we have to assume the exact function space. So here, let's assume that function space is of course linear, so like the simplest possible thing. But like it doesn't have to be finite dimensional. So basically, in the paper, it's written all with kernels. So in the end of the day, it can be like a universal kernel, and because the analysis of this particular algorithm, of this particular optimization algorithm, is dimension free, so it goes directly to the kernel cases. So it's just can be applied there. So basically, what will be like our function space in the end of the day? It will be this. So basically, we have this like design matrix F. We have some feature map which goes to from input to a vector of dimension d, like which is like our features. And then there is like a W, which is a parameter matrix. Then we actually want to. That's what we want to optimize with respect to. We want to learn to get W. So in case of infinite dimensions, it will be like one dimension of this will be infinite, so it will be like several vectors in the RKHS reproducing kernel Hilbert space. But I'm not going to like go there, so that's like stay finite dimensional, like for simplicity. Okay, so basically, like with this, for this thing, like it's kind of easy to compute stochastic gradient. So it's just like explicit form, because everything is quadratic. We just like derive it with respect to W and set to 0, and then we have the gradient. Yeah, sorry, there is plus here. That's my typo. Okay, so basically now we just like after like having said that, we just need to take a suitable like algorithm with convergence rate and like just plug it there, like combine the rates and get to the constants. But like it's not really. So basically, like what will be the algorithm like we're going to use? It will be like projected average SGD with constant step size. So basically, it's algorithm with finite horizon. So basically, you just tell me like we have n, like how many steps we are going to make, and then like we choose step size according to like which depends on like all the constants and n. Then we do like n steps like that, and then there will be. Like we'll have the rate. So basically, like what are the constants? Like okay, one constant bounds the distance to the optimum, so that's the ball on which we are projecting, and then there is the constant that bounds the expectation of the squared norm of the gradient.
And n is what?
N is
big n.
Big N is number of steps.
What is PD?
That's projection on the ball of radius or diameter d.
Oh, the ball centered where?
In terms of parameters. So basically, we have parameters, matrix of parameters. We have that space. Then I think it's all with respect to Frobenius norms, like in terms of matrices, kind of L2 norm if we vectorize everything. And then like there is a ball there of diameter d.
With center at 0?
Yeah, centered at 0, and then we project. That's the algorithm. So basically, like this projection is a substitute for regularization. So instead of having like L2 regularization with lambda parameter, we project like to control the norm. So basically, then there is like old result. So in the paper we cite like paper of 2006 or 2008, but like result goes like back like very old. It's like I was not able to trace the exact reference, but like there is a rate. So the people like Nemirovsky, Nesterov, Polyak, and so on, they've known this like for ages. So basically, the rate is not the rate is like 1 over square root n, and like this like two constants in the numerator d and n. And also like what this rate is. So basically, it's expectation on the surrogate risk at the averaged position, at the average position. So basically we have our iterators, we average them, and then we compute take of expectation with respect to everything. We get this. So basically now we need to combine this with the calibration functions and get everything. So basically, and here is like the nastiest part of the old theory, that we have to have like extra assumptions. Nothing can be done without some extra assumptions. So basically, what we need to assume is that optimization is well specified. So basically, what does this mean? I've even put that like in the red box to emphasize. So basically, it means that there exists a global minimum of this with respect to all measurable functions f that belongs to our function class. So, and that's like without that, like calibration business doesn't work. So basically, like with the finite dimensions, this sounds like a very strong assumption. We actually assume that the data is generated by the model, essentially that. So basically, if we go to universal kernels, it sounds much better because like universal kernel can approximate anything. So basically, then like we are happy. But also, it's not that easy because then the norm of the optimum stops being bounded, and then it's like we have to be like super careful with the optimization. Yes.
What is psi of x?
Psi of x is the feature map.
And why do you say that f should be measurable? Doesn't it follow from that representation?
Yes, but basically this is my assumptions that like so set of measurable all measurable functions is a very like big set. So maybe not, I forgot all measurable functions, but like that like can be like this f is there, so this f is taken care of explicitly. So like we don't care about f. So the problem is like the minimum of that with respect to all measurable functions have to be of this space. Otherwise, like results stop working, like stuff breaks. So basically, this, like in finite dimensions, this looks like very nasty. So basically, when we go to infinite dimensions with universal kernels, like where we can approximate any function, it starts looking a bit better. But still, like then there are problems with optimization, and like kind of like that result that I'm going to use, the simple result, doesn't work anymore. So like it's something more powerful have to be used. And anyway, like I'm not going to go there. I just don't know those results. Don't understand.
So once again, what do you mean by being very careful with optimization?
Okay, so basically, let's say we have a universal kernel, so we can approximate any function. But then, like when we are going to approximate that function, like some true function that we don't know, when we are going to build a sequence that converges to it, the norm of this sequence will be unbounded. Norm of the elements will grow unbounded. Mm-hmm. And optimization, like in that situation, is hard. Just like standard results don't apply. For example, like this result, it has d, and then d is infinite, and then BAM result doesn't work. So like there exists results that like specifically target this situation. Like Francis does stuff like that with some of his students, like to like kind of derive results. But anyway, then like what always happens is that like these assumptions are substituted with other assumptions which are less interpretable, and like just it's super hard to trace. And also like each step you go in this direction, rates becomes more complicated. So there are like way more symbols and way more constants. And since like here, like the goal is to compute constants, if there are like 10 of them, it's harder compared to when there are 2 of them. So basically, like what we've done, we've just taken this assumption, especially given that all the other papers, like which are somewhat similar, do the same. But actually, like that's like a big drawback, big problem of the analysis. Yeah, but okay. So basically now, like let's like having said that we have this assumption. Let's actually like compute the constants and like get to the rates, see what we get. So basically, if we just like after that we combine the rate with the calibration functions, basically we invert the rate, and then we can get this statement. So basically, to reach accuracy of epsilon on the true expected on the expected risk, on the expected actual population risk, we need like this number of iterations. So basically, what does this quantity depend on? It depends on d and m, like these quantities that were there like in the convergence rate, and calibration function. So basically, that's that kind of result that I promised you in the beginning. So the actual guarantee on the test error.
So calibration function raise this as epsilon squared, yeah? In simple
Yeah.
cases.
Yes.
So and it is squared once again. So it is 1 over epsilon in the 4th degree. So it's too big number, this t.
Yes, but like here, I don't care that much about the dependency of epsilon. So I care more about constants. So basically, if there is k, so basically if like this is like 1 over k, then like this thing will be like a k squared, and that's like that's the end. So I like, for example, like what we can do if we try to make the objective strongly convex, then we can get algorithm with like 1 over n, like convergence rate. It will be better, but like.
So a couple of millions doesn't matter here, okay?
Yeah, okay. Well, it depends like what epsilon you want. If you want 0.1, that sounds okay. If you want just 0.1. Yeah, but like here, so basically like I'm not developing new optimization techniques. I'm just the user, so I'm happy to use whatever I have. So like I was able to parse only the simplest one, so like that's what I'm using. So basically, if there is like a better optimization algorithm, which do exist, like the people are working on this like every day. So basically, like it can be like used here to get better rates. But I like what I'm going to do now is to actually like, once again like look at these constants, because like this one we've already like looked at. So basically, for 0 and loss it's bad, and for like block 0 and loss and Hamming loss it's good if the f is chosen in the proper way. So now what I'm going to do is to just compute this, like the remaining constants, to get the actually like the final result. And I'll compute those for the free losses I'm considering. So basically, what constants do we need to compute? It's the upper bound of the distance to the optimum, like to be able to project on the right ball, and also like bound on the gradients. So basically, I'm not going to show these things individually. It's just like the bound in the product, because the product, that's what appears in the rate. So basically, like this thing depends again on like many constants. So but this is yeah, we can set basically take D and M such that the product is like that. What are these constants? Like what is here? So basically, there are like two constants that we kind of have control of when we choose our surrogate. So one is the condition number of the matrix F. So if like by doing this, we can so basically intuitively, if this matrix is badly conditioned, then optimization is hard and like everything is slow. And if it's well conditioned, it's better. So it appears exactly in this way in the rate. And another quantity is the rank. So basically, the rank of F. The smaller rank, the better. So that's this, and then there are like two more quantities which you don't have control of. So those are like quantities which depend on the data. So like first one is the upper bound on the norm of the feature maps. It always appears in the results like that.
Yeah.
And the second one is the upper bound on the sum of the marginal probabilities as functions of features. So since we assume that problem is well specified, then this upper bound is there, so something. So in some sense, it's generalization of the equality that sum over q is less or equal than 1. So basically, like after doing this, let's finally compute.
And what is L max?
L max is the maximum value of the losses. It's 1. So it's the yeah.
It's a small number.
Yeah, it's a small number. That's the easiest one. L max is easy to deal with. Just formalize. Okay, so basically, what are the values? So basically, this is the, like for 0 and loss, it's like, okay, I haven't even like put the, I know the exact quantity, but it's like, it's kind of ugly, putting all this together, but it's big. So, but like, they are not surprised. So basically, 0 and loss is hard, and we are screwed in all the ways, all the possible places. Everything is bad. So at this place, it has to be like a drum. So basically, that's the key moment, what's going to happen for the good losses. And bam, it's actually good. So basically, we actually have that this product is big O of B, where B is like number of blocks. So it's a good one. So it's small. And for Hamming loss, we have this. which is not quite the number of their of length, but not of number of variables, number of variables cube, but still, it's like it's not exponential, it's polynomial. Okay, so that's basically it. That's the content. Yes, that's the end of the story. So we got the like complete bound, and it's not exponential for like the two like simple losses.
I still don't understand one thing, maybe a stupid question. You have conditional number here of matrix F, and you have a rank of
Yes.
matrix F. If F is degenerate, I mean it contains 0 singular values, then its conditioning number will be what? Will be plus infinity?
Yes.
Yeah, okay.
Doesn't
we
seem that-
will remove this like directions. It's like, okay, so F is a part of the surrogate, so it doesn't really depend on the data. So we are like the people who model the thing like select F. So please don't add degenerate directions. I think that probably this could be like there should be like a workaround on this. So like we will just consider the ratio to the smallest non-zero singular value. This probably could be like worked out, but I haven't done that. So just please don't add.
Yeah, but this means that kappa of F probably some alternative, but not exactly conditioning number, right?
Well,
Because
like,
we
I assume
exclude
that
all zeros.
F is of rank R, so there are no degenerate columns, and then it's condition number. So it's just
R is rank of what?
Of F.
Of F.
so basically F is R times K, so K
Okay.
times R. So it's the rank.
Mhm.
It's the rank. So yeah.
Okay, okay.
Like for this particular thing, I'm not worried too much. I think this can be like easily worked out. It will just like add complexity, not at the key place. Okay, so basically that's the whole story. Let me like quickly conclude. So basically, the whole like point of doing this was to like present like kind of a theoretical approach to like trying to choose a surrogate, to understand what is a good surrogate, and like to get some way other than pure empirical studies to like to get a surrogate. Then also like we discovered that for structured prediction consistency is not enough. So consistency is a good property, but like it's not enough. And maybe like we've seen examples, like I've shown you like at one of the plots. So it can be that if the surrogate is not consistent, it can still allow you to achieve certain accuracy, not arbitrarily small accuracy, but certain good, maybe good accuracy, but like much faster. So it might be worth considering even non-consistent loss. But like for that case, I don't have any like smart theoretical result to show you.
Anton,
Yes.
again, one stupid question. And at what part of the talk you were selecting the surrogate?
The quadratic surrogate,
But you have fixed it.
like the F, the matrix F is also like design matrix.
But matrix F is it defines the score function, right?
Yes, so it's
Not the
only-
surrogate. Is the score function.
Yeah,
The score
okay.
function is different from surrogate. So you were
Yes.
analyzing the score function,
Yeah.
but you were not analyzing the surrogate. The surrogate was always fixed.
Yeah, okay, I agree. You can look at it this way. It's only like for quadratic surrogate because you couldn't prove anything else. So, yes. It's very interesting direction to go for, like trying to do something else. But I'm afraid with my current proof techniques, it's not easy. So something has to be changed there. Maybe we should have to go from high school math to like undergrad level math, like use something smarter compared to what I used. Possible.
And you're using just high school math?
Yes, like actually like those like the hardest results, like exact computation of this thing are like high school math. So there is nothing there, like just not able to like use any like knowledge I get, just like direct computation. That was the way. Okay. So anyway, like we've shown that like calibration functions can be computed sometimes. So it's not hopeless to try to compute them. Maybe sometimes like we can get like even relatively general bounds. Well, not as general as we would want to, but like relatively general, and it's still, I think it's still interesting. And then like we try to like define the scale of the surrogate by connecting to the optimization. This piece I've never seen before. So because usually people don't divide by k and then they're happy, but when k goes but then like the surrogate they're optimizing, like the values are like exponentially big, so it's hard. So basically, maybe like this like way to just use optimization algorithm as a like scaling factor and like to get the right constants, the right scaling is like an interesting way. I think this idea can be like applied somewhere else. And also like in all of that we had to be like super careful with constants because like exponential quantities pop up here and there, and then they can kill any rate. And so basically, like future plans is to like try to bound calibration functions and constants for more losses. So here, like we do have
For
some.
which one, for example?
Yeah,
What's the idea?
logistic, like something like logistic. So basically,
That you can't calculate anything for logistics.
well, maybe we could bound something like well, it's like.
By just Jekyll and Jordan bound your logistic with quadratic and
Yeah, maybe that's the way. That's the way. Yeah. Okay. Like so, basically, like since now we know almost everything about quadratic, we can like if we can bound something with quadratic, like we're happy. Yeah, but like it's future work. So basically, like try to generalize analysis for other surrogates. Maybe this mostly applies to optimization part because that was also done like only for the quadratic. So maybe there is like a more principal way to compute this constants and not to have, because like computing these constants for each surrogate is kind of annoying, and so basically like maybe some more general bound or like specific optimization algorithm which is good as a scaling factor, like with easy constants, that would be good. And also like the final point is to try to make this practical. So, like in my defense, like to make it about practice, I can say that there is a research direction which is like very related to this and it's kind of practical. So basically it's called like input-output kernel ridge regression. Like this like it's the whole like set of methods. So basically what they do, they have an objective which does not depend on the loss, but which matches like feature maps of outputs and inputs in the RKHS. So basically, and then when they get their like estimator for that, they apply the loss and do like solve the inference problem. So basically, if we consider a finite data set instead of doing SGD and like consider like just a finite data set and then solve the regular way, you go the regular way with kernels, like compute gram metrics, invert stuff, then we get exactly the same estimator as they do. So it's like just quadratic estimator with kernels. Their approach kind of works. So like in that case, ours should also work. This will be like the same estimator. The difference is that they are all the like regret bounds they have are like exponentially small. They just like put like some norm in the bound and don't analyze how big or small that is. So for structured prediction, it doesn't really work. So basically, another point, but it's not also. If that was that simple, I would have already done this, but like it's not like that, because if we go away from like online SGD, then we have to apply learning theory and like get sample complexity bounds, and that's not easy. That's another layer of complication which I couldn't get through like now.
So above high level, high school math.
Yeah, like that's you know, like when I see like actual Hilbert faces, it's complicated. Okay, so basically that's it. Thanks a lot.
Okay, any questions? Any questions?
Yes.
So, what is the problem with calibration functions to be exponentially small? Is it practical? Reasons like you can run SGD because...
Yeah, so basically what is calibration function? It tells you like which accuracy you need on the optimization problem you are actually solving to get the correct accuracy on the optimization problem you actually want. So it connects like the two. So if it's exponentially small, it means that like for a reasonable accuracy like that you request, you have to solve the optimization problem exponentially well. And then like your convergence rate will blow up. You will just not be able to achieve that accuracy.
Especially when you're dealing with SGD.
Yeah, especially SGD, and like you have finite samples, so it's like what I've seen, what I've somewhat shown that like complexity of calibration function is like somewhat correlated with complexity of constants in optimization. So for if the loss is hard, like everything breaks. So like for zero loss, nothing works. But like it's kind of meaningful if you have like say like 10 to 23 classes. Then like optimizing like exact class is maybe not a good idea to do that. It's like kind of intuitive on its own. So basically, our like byproduct of what we've done is like one way to like formalize that intuition. Yes.
How do you do inference for a quadratic surrogate?
Okay, that's a very good question. So basically, like I've put that under the carpet, but like I'm happy to explain this piece. So basically, just open the gradient. I need to show the gradient. So basically, to actually implement this, there are like several like tricky pieces. First, like some of these metrics are like have k in the dimensionality, so it has to be like multiplication has to be done. The good news is that k is in the right place. It's like inside. So we, like to be able to implement this, we have to be able to compute f transpose f, where like k is inside, and we have to be able to compute f transpose L, like this thing, where like also like dimension k is inside. Like for all the losses I've used, those are analytic, so it's like easy to just compute.
Mm-hmm.
But like if the losses are more complicated, like some inference algorithm can be there. But like this thing has to be computed once, it's just there. And this thing, it does not depend on x, it does not depend on data. It's like it only depends on the label, so it's also like somewhat kind of maybe easier inference algorithm. So, but anyway, like those have to implement this gradient, compute this stochastic gradient. Those have to be computed. Then the next piece is the actual inference. So what is the actual inference? The actual inference will be, so basically you need to compute max with respect to y of f w phi x. So basically here again, like this will be like say like we have x. Then, like, if we are not using kernels, we just computing this explicitly. Like, those are like small matrices. If we are like using kernels, this will be like inside like regular like kernel expressions with metrics, but like with the regular kernel expressions, yes. But like still, like we will have to optimize in the end f times something. And like to do this maximum, yes, we will have to use the structure of f. So basically, a structure of f somehow, for example, if it gives you like factorization assumptions, then we can do like regular inference algorithms. So and if nothing is there, then sorry.
And what about the situation when we can find maximum approximately?
Well, then like it's like as usual. If you have control on how approximate you are, then you can like combine this with the bounds and get like a result which controls for this approximation. If you have no guarantees, then like no guarantees. Yeah, but if we,
that's
like,
the usual case.
Yeah, that's the thing. Like this analysis has like many stages, and if at one stage you lose connection, then you cannot say anything anymore. There is no guarantees.
So any questions? If not, then let us pick the speaker again.